Our today's speaker is Uisun, who will tell us about Borel-Moore homology and convolution in convolution.
Let me introduce the subject. It's about the Borel-Moore homology. Well, although I don't know why this type of things are very important yet, but so far I've understood that what we want to do in this literature is that we basically want to study representation of an algebra A given an algebra A in a geometric way. And geometric way means we want to identify such an algebra as a geometrically popping out objects. And in this context, we want to identify A as a so-called convolution algebra. Of a correspondence C, which means a subset of M cross M for a smooth, complex algebraic variety M. Such a correspondence is called idempotent if the composition is itself, where the composition means the composition of correspondences. And we'll see in this case, H star Z as a C vector space admits an algebra structure, associative algebra structure, which we will call the convolution algebra. Yeah, it can be a graph of a map, or it can be just a closed subset. So this is like a generalization of a map, which can be like multi-value in some sense. Yeah. So it's just a subset, closed subset. Of course, you can easily see that graphs are obviously correspondences, and the composition of graphs are as a correspondences are a composition of maps. So to define and prove some properties of Borel-Moore homology, we'll introduce and use some knowledge of six-functor formalism. And I will just briefly review some features. And all the spaces and maps are assumed to be very good so that we will have good finite dimensional conditions so that we have functors of bounded constructible sheaves. So roughly for a space, we will assign a derived category of bounded constructible complexes, which is triangulated. And for each maps of such spaces, we will assign a bunch of maps, functors that goes back and forth twice. So there's a direct image functor and a pre-image functor. Let's use inverse here. And proper direct image functor, it's called like as lower shriek sometimes, and the upper shriek functor. The location of stars or this shriek marks are they mean we will have a functoriality like this. And they are when they are like composable, of course. And they satisfy a jointness condition. This, and also there's a functor, which makes dx as a dx monoidal category. Also, the internal Hom functor. These two satisfy the adjointness relation as well.
Derived.
Sorry?
Is tensor product also derived?
They are all derived.
Yeah.
I'll just write. I'll just omit our derived notation.
Wait,
Well,
our home.
Yeah, our home. Oh, sorry. Okay. Okay. Only for our home because it's like confusing. Yeah. So all of them are actually derived functors from that comes from the functors of just complexes of sheaves. Okay, also they satisfy some important conditions, namely phase change and whenever we have a pullback diagram like this, we have natural isomorphism of functors due to we have two ways to go from here to here, right? This way, but strict and usual. And they are naturally isomorphic like this. G1 strict to F1. And a joint functor of these yields also this kind of natural isomorphisms.
What if you like the original of vegan category? Yeah, of course, sorry. The community like
No, there are it is a Hilbert diagram of spaces. Yeah.
oh sorry. Yes, thank you.
Also, projection formula. Whenever we have this kind of expression, we have a natural isomorphism. Mr. Homology. So in some sense, we can consider this map, this functor, here ui, as a dy linear. So this means dx has a dy action using the pullback or inverse image, and f lower street commutes with this kind of action like this. Okay, so also we have natural isomorphism. And we can identify homology groups of our home, seeing a home set of n to shifted G. So when I write R large home, then this means it's a home set of Fn, home set of objects in the derived category. Okay, so any questions so far?
So exactly again, so it's so little home is internal and large
Yeah,
home is like just home.
Yeah, it's just home. Yeah. I wrote the internal home like this with the underlying bar.
Yeah.
And this is
Cortex of
this is in dx. And this is just the this is just in our process. Oh, and I forgot to mention this. We will use the triangulated category of complex of sheaves, coefficient C. We can use other coefficients, but we'll use C.
Wait, sorry, can I, so our home FG is object of D of X, like a complex of
Yes.
sheaves on X, and HE is P homology of it as a complex, so it's a sheaf on X.
It's not a sheaf.
No, left side. I got confused about the left side. What's happening? So you.
Sorry. Okay, the global section.
P derived.
Yeah, P derived functor of the global section. Yeah, I forgot this. Yeah, you're right. Yeah, if we just take the P homology, then we'll get a sheaf.
Yeah, and yeah, so it's just a vector space, but on the right, so you're taking derived home, so it's like a complex. Or do we take zero homology? Why is it? Why is it not a complex?
Well, we can just take this, then I think it will be clear. This is just a derived constant.
Okay, yeah, just constant. Okay, yeah.
Yes. Okay. Sorry,
What's P derived?
you mean this one?
Yeah.
Oh,
It's a, like, chain complex still takes a P.
yeah.
Just take it.
When we take gamma, then this means
It's a derived.
derived global section function,
So
and we take HT of that. Yeah.
Oh, it's the video is like one P.
Yeah.
Sorry, could you maybe stay on the right side? If you
They on the right side?
yeah, you have upper.
Oh, I see. So there's a special sheaf, complex of sheaves called the dualizing sheaf for each space. So for each space X, we'll define AX to be just a trivial map, constant map from X to the point. Then the inverse image functor of C, the constant sheaf on the point, which is just the complex of vector spaces. This is defined as a constant sheaf. Can be defined better, but yeah, we have this constant sheaf. And when we do the derived upper string functor, then we'll get so-called dualizing. Well, this these maps are very important and useful in some sense because, well, it's technically very easy to show, but when we do the lower street, lower star, then we'll get a counter from EX to the point is the derived category of vector spaces. We'll just write B. Then what you get is actually the derived section, derived global section functor. And also, when we take the lower street, then we also get this direction map functor, which is a derived functor of global section with complex support. And there are also other ways to to formulate the derived global section functor. Namely, we have our home from the constant sheet to add isomorphic to the global section functor. Well, this comes from just the basic fact that the in a module, our module, we have the sum of Rm isomorphic to n naturally. This is just a last generalization of this fact.
We are in constructible shifts, yes?
Yes.
All this time.
Yeah, we are always in constructible shapes, but that will actually does not matter. That does not matter in this talk.
Okay.
Yeah. And the dualizing sheaves can be used to deal with the duality, dual functors. Mainly, we have interesting duality, called Verdier duality. So we have a functor from dx off to dx, given by mapping f to df, which is defined by Arham of f to omega s. Then, because we are working in constructible shapes, we have d squared f isomorphic to f. And we also have some kind of interesting intertwining properties like the f lower shape isomorphic to the lower star f lower star d, and upper star isomorphic to upper street, and so on.
Small palm or big palm?
Yes.
Okay.
Also, we can Also, for F, we can identify these as some kind of tensor product of df and g, where this tensor product is defined by I upper streak of P1 inverse F, tensor product P2 inverse P, where P1 and P2 are given by this these map, and I is just a diagonal map. So if we had inverse, upper star here, then we will get we'll get usual tensor product, but because of this upper streak, we have another functor given defined as exceptional tensor product, and that exceptional tensor product makes our home in this sorry, that exceptional tensor product can be used to define our home like this. And in this way, the D intertwines tensor product and exceptional tensor product, which means EF tensor product DG, DFG with EF exceptional tensor product region. So this variedual functor, we will call this the variedual functor, intertwines these interesting and important functors in this way. Any questions so far? So far, I'm just stating the results from six functor formalism, but it will be useful in studying Borel-Moore Homology. So for closed subsets, we also have some kind of interesting basic sheaves called we have some kind of I upper streak and I lower upper star and I lower streak. Then we'll get functor like this. Sorry. And I upper star, I lower streak. I upper streak, I lower star. Then we'll get a functor R gamma C.
Sorry, in definition of tensor streak tensor should one of the like upper star be upper streak. Like maybe I think it should be P2 upper streak. The definition like that streak tensor.
Oh, here?
Yeah. Oh yeah.
Well, it's actually defined as a streak of Fox tensor product G. So think it should be inverse star also here.
Wow, maybe worse.
Yeah. Oh, sorry. We can just apply this functor on any sheaf F, and we get this. And the important fact about this is that we have our home of the Z we have is isomorphic to R comma Z. And these functors can be naturally identified as a heap of sections of R supported in Z. So if we take the global section functor, then we'll have something like this. Z is locally closed or open or closed subset. Then if we take open subset, then and take global section of this, then we'll get R gamma U of that. So in some sense, these functors serve as a Uneda sheaf.
Forms should be the same.
Where?
Is lower form here with this? But
So it should be smaller home.
This one? Yeah, it's a small home.
Next one's big home.
Yeah, this is big home. Maybe I'll just write like this, and this will be just a derived home.
Sheaf of sections of F. Okay. Yeah, but so in the second line, so F is a sheaf on X, right?
Yes.
Wait, is it true that if you take sheaf on X, restricted and shrink push forward, you get the same? I'm pretty sure if it's doesn't have many sections, so
Sorry.
Is it true? If you take pull back to Z and then shrink push forward, I don't think you get the same.
It's not same.
Yeah, but
that was erased. Sorry, this is a definition. The FZ. So I'm defining a new sheaf FZ.
Yes.
And CZ is a constant sheaf, and then that applied this construction.
Yeah.
Yeah, so thank you.
Okay.
Okay. Can I move on?
Yeah, just maybe does it have any so like R gamma Z is sheaf of sections of F supporting Z, but what is FZ? Like, does it have any kind of description?
Oh yeah, I know some easy description of that. Let's just consider a non-derived case, because it turns out this actually comes from the non-derived functor.
Yes.
and that functor is exact, so we can just apply it by term.
Yeah.
So for just a sheaf F, and we can consider a sheaf as a étale map like this. This is our space, and these are fibers, and we have all the sections in the étale space of the sheaf.
Okay.
And we can interpret the sheaf as being a continuous section on each open subset, right?
Okay.
And FC is just taking the Z part. We can restrict to the inverse image,
Okay.
and then we have the space like this. This is just the inverse image, and take the union with the X.
Okay.
Let's say pi inverse Z union X. Then there is a unique topology on this space that makes this natural pi tilde map that maps this to the base, and X stays as identity. And there's a unique topology on this map to be to make pi tilde at all, local homeomorphism. Namely, we can take each open subspace and make this kind of some seemingly disconnected sets as a basis.
Okay.
Yeah, then it will be a local homeomorphism.
Okay.
Yeah, then this sheaf is the FC. So in some sense, I call that sheaf a truncated sheaf because I truncated the C part and just attached to the zero section.
Yeah. Well, yeah, so like for Z open, it's something, if Z is open, it's something easy, yes, it's like restriction of F or something. Okay, well, maybe we can discuss it later, this image.
Yeah. Actually, when Z is closed, then we have easier interpretation of that.
Okay.
Yeah, because this is defined as a lower shriek, and that lower shriek gets along with global section functor only if it's proper. So,
Okay.
or there's an easier description of this being a unique functor that restricts to Z to be a restriction of Z and restricts to the complement, restricts to 0 at the complement like this. So all the stocks at not in Z vanishes, and the stocks in Z is just the same as F.
Okay.
Yeah. So far, we've discussed the lower streak and upper stars and lower stars. But for some important cases, we can actually calculate them. So, for example, when F is proper, then F, sorry, for this, we have a natural map from F lower street to F lower star. It comes from non-derived functors of F of these, which is just a F lower push forward with complex support, sorry, proper support, and this is an isomorphism. Consider an isomorphism. If F restricted to support of F is, in particular, this is always isomorphism if F is proper. Second case, if F is an open embedding, then upper star and lower star, I'm sorry, upper star and upper street are naturally isomorphic. So we can exchange upper star and upper street in this case. Also, if F is a closed embedding, closed embedding of manifolds. Here, in this case, we assume X and Y to be a smooth manifold. And the normal bundle is orientable. Then we have a natural isomorphism of upper street to be upper star with shifts minus t, where t is dimension x minus dimension 1, 4-dimensional. And in that case, if F is orientable, is an orientable smooth fiber bundle, then we also have this isomorphism, where B is a 5-dimensional equal dimension. So
Sorry, what is orientable fiber bundle? Orientable.
you're asking what is the definition of orientable fiber bundle?
Yeah.
So roughly it just means all the fibers are oriented So fiber bundles are locally trivial.
Yes.
Sorry, locally trivial
Yeah.
for clarity.
What's the setting here? Are we working with like complex manifold or?
Oh, in this case, we are only working on smooth no further conditions, I guess. But in 3 and 4, we are working on smooth manifolds.
Sometimes maybe measure this like so everything here is like controllable shapes. It's not like random shapes, right?
Yeah, constructive shapes.
So everything's
Yeah.
real shapes, like shapes on that.
Yes. Yeah. Or like varieties.
Yeah, but on varieties, well, I mean, same question I'm talking about like random shapes.
It's just no careers.
Yeah.
I mean, yeah.
Because like the convention at upper star is kind of confusing, right? Because
Yeah.
Tensor with like F universe, all that.
Yeah, you're right. I'm so far I'm using F upper star, but yeah,
It's actually F universe.
yeah, it's actually F inverse.
But I mean, if it's not an OX module, then there is no confusion.
Yeah, but sometimes it can be confusing. Yeah.
I don't think any constructible shift can be OX module just because.
Yeah.
I mean, except 0, 1.
Yeah, we are working on constructible shift, not a or small or like coherence. Okay. So in these cases, we can just replace upper star or lower upper strip or lower strip to some kind of upper stars or lower stars. And especially 3 and 4 comes from just the analyzing vector bundle case, fiber bundle case, locally just a Z cross F. Namely, the map embeds 0 section into Z cross F, or the map projects Z cross F to Z. Okay, now I can define what the Borel-Moore homology is. Actually, I can define a best.
It's okay.
Is okay?
Yeah.
Define other like homology or cohomologies using sheaves, namely Borel-Moore homology on X will be defined as a ith homology of R gamma X omega X. So H minus I. This will be some kind of in functors. We'll have AX inverse, sorry, AX lower star, AX upper streak of C. And the singular cohomology will be defined as a cohomology group of R gamma of X, C, X. So this will be the cohomology of AX lower star, AX upper star of C. Similarly, we can define the singular homology and homology with compact support defined as a H minus I of AX lower streak, AX upper streak of C, and HI of AX lower streak and AX upper streak. Just a torch, please.
But like in the last definition, to me, the British was like the Euro, like.
Yes, yes. Yeah, so you mean the fourth one?
Yes.
So this actually means we are taking R gamma I of X omega X, right? Yeah. This is why,
Gamma CR.
yeah, gamma CI.
Why is, I saw the usual definition of like complex polynomial. Homology is arga, like the complex polynomial homology of constant shape, not polygon. Because like the equivalence of
Oh, yeah, yeah.
only works for many.
Yeah, I think I mixed these two. Let me check.
Okay.
Yeah,
It
yeah.
should, in here should be star push forward.
Yeah, the
Single
third
version,
one
you
should
should
already
already
at
a slower start. Wait.
Yeah.
No, I mean, for the third one. is
Third
it
one?
Shoot push forward or start push forward?
So all the shriek. Yeah, they
Why
are.
all strict? But
It shouldn't be any single.
but if like X has singularity, then the dualizing shape might be. Anyway, you're taking the complex polynomial, a section of dualizing shape.
Yes.
Consider. I'm not sure if that's thing along. At least one of the correct definitions is lower side, upper side. Like a single. One. Oh.
So sorry, are you talking about this one?
Oh, wait, it's all.
Yeah, it's homology, yeah.
Well,
It's singular homology, yeah. Minus I of this one. Yeah, and
Oh,
singular
yeah.
homology is, yeah. Sorry, should I say like here? Yeah. I think now it's correct.
I guess easy way to remember is the top one and the bottom one argument.
Yeah.
All right.
They are related by universal coefficient theorem. Yeah, and these two are related. I think it's okay now. Can I move on? Yeah. And for Borel-Moore homology, we have a Poincaré drawn as well. Let A I Z into M be a closed subset, and M is a smooth orientable manifold. For example, smooth complex algebraic variety. Then we'll define the local homology group as R gamma Z, HI of R gamma Z of M of the constant sheaf. Then this local cohomology group is isomorphic to I, M minus I of Z, where M is a dimension, is the dimension of M. Okay, let's prove this. So R gamma Z, we'll just omit HI and take HI later. So we will prove this on R gamma Z. And this is R hom of CM I star I trig of CM. This is the definition of R gamma Z. And we can use I promise not to use R hom. And this is hom of C Z I upper trig CM. Because I lower star goes to I upper star here, and I upper star of CM is just CZ. And then we get CZ, and I upper streak of CM is actually isomorphic to I upper streak of omega M with negative shift, because M mapping to point is a smooth fiber bundle with orientable orientation, orientable smooth fiber bundle. And I said in this case, a upper streak of C, which is the dualizing sheaf. And this is same as the A upper star C with a shift. And this is just a constant sheaf with shift. D is M, where M is the dimension of manifold. So we can just use the upper streak. Omega M is defined by upper streak of constant sheaf. So it's just a commutes with I upper streak. And we get CZ omega Z minus M. And this is just hom of CZ omega Z shifted by minus M. So by taking HI here and here, we get HIZ M isomorphic to H minus I minus M of x omega z, z omega z. This is, sorry, I minus m. This is, by definition, m minus I, Borel-Moore homology. Because of the shift, when we take hi, then this will be hi minus m.
There should be dm on the
Oh, yeah. When I just write this, it will mean bm. Yeah, yeah. So, in particular, when we take c equals to m, then this will say hi of m is isomorphic. Sorry, hi of m is hi of m is isomorphic to m minus I of m. Yeah. So if M is a orientable connected manifold, we have HM isomorphic to H0 to C. And the class corresponding to 1 will be denoted as like this, and it will be called the monodic class. So we didn't assume M to be compact, and one of the key features of Borel-Moore homology is that it has the fundamental class wherever it's orientable, and it does not need to be compact. And for some special maps, we'll have the induced lower star and upper star. There can be a shift like this. In some special cases I mentioned a while ago, namely H star x, R gamma of x omega x will be AX upper street, AX lower star C. We have these two maps. And obviously, this is just a constant map, so this diagram commutes. And AX, so AX can be decomposed as F and AY. So this is AY lower street, F lower star, F lower star, F upper street, AX, AY upper street.
So second map, you mean, like, from H star Y to H star X, H star plus B X, not one. The second map.
Yeah, X. Yeah.
Is it still fiber bundle?
Yeah. When F is proper in this case, when F is a open merge, open embedding, or fiber bundle, or embedding of closed manifold with orientable normal bundle. You remember the 4 cases when we can actually compute these upper street in those cases. So in general, let's just consider this. Then we want to give a map from I, y, omega y, which is a y star and y grid. So this map depends on this map is actually coming from either this direction or this direction. But this direction is defined only when F lower star, F upper star is up to shift. Sorry. Yeah. This map is well defined because F lower star lower streak is left adjoint to F upper streak. And this map is well defined when up to shift when we have this. Because F lower star is right adjoint to F upper star.
So why would we shift here? We will never have a job there.
So we want this map up to shift, and this will come from in some special cases this map. And yeah, F upper star and F upper streak is in general different, but in our special cases we have this identification.
Like submersion.
Yeah, submersion or inclusion of closed oriented manifolds or open embed.
If I use those cases at upper street are different.
I think open.
Yeah, but it's up to shift.
Only that is universal.
I mean, when F is a
No, I think only you talked only about bundle and close embedding. I think open embedding is just wrong because F upper shriek here is in this case derived and is I mean it can be a thing from a usual factor which is sections.
No, if somebody adding the half upper street is half upper star.
Yeah,
open balance. Yes.
yeah. So in that case, D equals to 0.
Yeah.
Oh, sorry,
It's
it's
submerged.
yeah, sorry. Okay.
And I'm just mentioning this whenever we have this kind of identification, then we can construct this map up to shift. So we get this kind of yeah.
You just take conquer duality everywhere.
Yeah, you can also do that.
Our first map will just be pullback. And the second one will be like fiber integration.
Yes. And we have also analogous construction of products. So remember, when we have an internal form, then we have some kind of composition. these brackets are just general internal hom. So alpha, beta mapping to the composition. And in this way, we can have our hom f, r hom gh, r hom fg to r hom fh. And if we take the hi's homology, then we'll get hi of hom of gh I tensor hom of f g v to hom of f to h I plus v, which is just a composition of homomorphisms, such as like if we have g h I and f to gj, then we can compose these two. We have f vi to hi plus v. So we will call these kind of products for compositions unit product. And in this way, we can get intersection product or a cup product in the following way. For Z1 and Z2, in a smooth orientable manifold M, we have HZ1 F to HZ2 M to HC1 intersection Z2 I plus J. And this is just given by when we have this map, this is just a hom of CZ1. This is a truncated shift to the constant shift shifted by I, and same here. So we get CZ1 to CMI and CZ2 to CMJ. And we can take the tensor product and get this map, and this is CZ1 intersection C2. So we get a map here. Because it is defined using tensor product, we have good properties like associativity. And using Poincare duality, we get H of H star of Z1, H star of Z2, HI to HI plus J minus D of Z1 intersection Z2.
tensor product of CZ1 and CZ2, CZ1, CZ2.
Yes, yes. It's because
I mean, I derived and then go to.
oh, it does not need to be derived because in general, CZ tensor F is isomorphic to FC.
Yeah, but so here that's a product in a given category of instructible shapes. Or
Derived tensor product here, yeah. But you can just take it. It can just be just tensor product.
CZ is like flat, so tensor with CZ is exact.
Yeah.
About they were for like constant shape. Like taking local way where at this function is exact. So you don't need to derive or you can.
It's I'm here in
Is everything okay? Yeah. So now we'll define the convolution product. Suppose we're given smooth that M1, M2, M3 are smooth orientable manifolds. And we have these maps, Mi plus Mj. We denote this MPIJ. And suppose we have a closed subset, which means it's a correspondence in M1 plus M2. This is in M2 plus M3. Then we have H C12 and HC23. And we'll define the convolution. This will map to Z12, convolution Z23, composition Z23, and Ij to I plus J minus D, where D equals to the dimension of M2. And this will map alpha and beta to first map to P1 to in star alpha and P2, 3 star beta. And tensor product, where P1, 2 star alpha and P2, 3 star beta are all in the they are in H C12 cross M3, H C2 M1 cross E23. And we can take the intersection product, because they are all closed subsets of M1, M2, and 3. And then we can take the lower star of P1, 3 by M1, M2, M3 to M1, M3. Then we will get the intersection of these two. So, and the intersection of these two and mapping to P1, 3, the image of that will be the composition. So P1, 3 of C1, 2, P1, 2 inverse C1, 2 intersection P2, 3 inverse C2, 3.
Sorry, what was D here? Like H in so H I Z1, H I Z2.
Maybe
No, on the upper left,
upper left,
upper right.
upper right. This one?
Yeah, but upper in general case, when you define this operation from H I Z1, then the H G Z2. No, even higher. Yeah.
This one?
Yeah, and to the right.
Yeah, it is defined by using Poincare duality.
Yeah, but what is
Oh. E is just a dimension of M. Yeah, dimension of M. Because we use Poincare duality here, and we have D minus star shift. Yeah.
And so this notation intersection is what we define. So here we use B this intersection in homology. And this is
This one?
Yeah. You did not define this symbol. Yeah, you did not define that. You want to start out? Yeah.
This one?
I think it is.
Huh? Yeah, it's just the intersection. Oh, sorry. Yeah, we will define the intersection product using Poincare duality, and we'll denote this.
Okay. Yes, and what does then so D is dimension M here, but on the lower it's not dimension of M, it's dimension of M2.
Yeah, it's because
You're intersecting it.
yeah, intersecting makes minus D, and the other things does not.
But here you define D as a dimension of the ambient space, which is M1 cross M2 cross M3. But here you write that D is just dimension of M2. So why the difference?
Oh, I see. So I think it comes from these two. Yeah, these two has shifts. Yeah. Yeah, thank you for putting it.
Do you want to compose C2 to?
This one.
No, like the state inside H, like the space.
This one?
Do you want to, did you define this notation?
Yeah, here.
Oh.
Yeah.
Yeah.
Yeah, and it's just the composition of
Yeah.
the correspondences.
And here assume that P13 is proper when restricted to.
Yeah. Restricted to P12 inverse C12, P23 inverse C23 is proper. But this is a necessary condition to define the convolution problem.
But I guess, so when you're saying, I mean, the stuff you wrote in the last step, that a priori is a homology class, right? So what do you mean by H of that thing?
This one?
Sorry, you wrote equal to projection of to the right. Yeah, this whole thing, that's a homology.
This whole
class.
thing?
No, No,
This-
right there, yes.
Oh, yeah,
That's a
this is not homology class, this is just a set theoretic operation.
Oh.
Yeah. This is an image, this is the inverse image.
No, but you. What?
Like CIJ is some subset.
So.
Yeah, it's a subset, yeah. Yeah, but they are really related, yeah, as you can see.
Why won't you make it a subset into homology?
Subset into homology?
No, just for short information, it's like P1 free that goes from this thing to T1 to C.
Yeah, so P1, 2. Any questions? Oh,
I think I just got confused when you wrote like intersection for both, for homology and for sets, but it's okay. I'm
okay.
confused.
So here I'm using the restriction of P1, 2 into this is inverse image of this is vibration, and so here also, and I use the properness of this restriction, so we have all these maps well defined. Yeah, and yeah, I don't have enough time to say this, but the convolution product is associative. We can prove this using the projection formula of cubes. And so when we have proper morphism of smooth manifolds, then we can consider the pullback Z as a closed subset of M plus M.
Over M. M goes.
Yeah, and yeah. Then you can easily check that this Z, the correspondence is identical. So because of the associativity, we have H star Z, H star Z to H star Z. And this is a associative algebra structure on H star Z. Whenever it's idempotent, but yeah. And I think my time is like almost, I mean, already 2 minutes over, but can I?
Oh, no, 5 minutes.
Yeah, right.
So it's-
Well, so we can calculate this using some kind of knowledges of like subanalytic chains or so, but so that's why we make this kind of definition, but we can also define this by using sheaf theory. So my last theorem today that that L that F M to N proper M is a complex manifold, and L to be at lower star of C M M, where M is the complex dimension of M, so half of the real dimension. Then H lower star of C is isomorphic to X algebra of LL. Remember, when we have X I of LL, then we can define the unit product, and that unit product will make this into algebra because we have associativity. And And this theorem says this convolution algebra is actually up to shift, up to grading isomorphic to this X algebra. And I'll just briefly say why this is true. We'll just prove that it is isomorphic as a vector space, as vector spaces. Just take DL, the dual, then it is a DF lower streak, a lower star of C M M. Then this will be F lower streak of omega M minus M by commuting the D and the functors. And this will be, since F is a proper map, we have a lower streak, a lower star of omega M minus M. And since omega M is isomorphic to C M 2M, so we get lower star C M M. So again, isomorphic to L. Now, consider we have H I of C, M minus I of C, which corresponds to 2M minus I of C corresponds to C Z into Cn plus M. And consider the diagram. Given by this, and this is a Kullback diagram. So CZ is a truncated shift, so we can actually make it like this. And using the jointness, we have giving alpha is one corresponds to I upper streak of Cn plus M. And also CZ is J P upper star of Cn. So this also corresponds to Cn to P lower star I upper streak of Cn plus M. And then we can use the base change. So we get delta upper streak F plus F lower star C M plus M. And we get delta upper streak L tensor product dots product L with shifts. I'll just ignore the shifts. And this box tensor product is actually equivalent to L dual because L is equivalent to L dual, and the exceptional tensor product L. So given alpha, one corresponds to Cn to L dual L, and this is isomorphic to R hom LL. And this means Cn to R hom LL, which is equivalent to hom of LL. Okay, so when we are given order P, then we will actually looking at shifts from P.
So can we keep all lower so we can assume that we can.
Oh, I'm sorry.
No, lower.
Lower.
That's it.
Oh, yeah.
Yeah, that's it.
So I just proved that the up to grade shifts, H lower star of Z is equivalent to X alpha. And when if you track the grades, and then you get this 2n minus 5. And it's a separate theorem that the algebra structure here corresponds to the algebra structure of the convolution algebra. Okay.
Alright, okay, so you prove that CN is the same as R hom for the hom sheet. Why does that, what is the last equivalence?
So I use that this is equivalent to R home,
Yeah,
and this is equivalent to this because it's just the
Sure.
definition of this.
I just don't understand the last, what is the last?
This one?
No, the
This one.
outside, yeah, what is?
Yeah. So Cn is just a constant shift on n, and R home LL is a shift complex of shifts on n.
Yeah.
So Cn giving a p shifted map to constant shift to something is equivalent to giving a
Yeah.
global global section. So in this way, we can analyze the convolution product, which can be calculated very well in to some sheaf periodic construction, and this is very useful to analyze the representation of this convolution algebra using BBD decomposition theorem. And using this, we can like analyze the representation using geometry. Okay. I think that's
How we, so we want like representations of like HI,
yes.
like top dimension or like any dimension? Okay, that's all. Okay, that's all, like how will we do that, like use? geometry to-
Briefly, we have the decomposition theorem for push forward of perverse sheaf, and RL is a perverse sheaf, and we can decompose the push forward with like some intersection complexes and factors, and because our A, which is the convolution algebra, is just an X of that L and L, we can just use the properties of intersection complexes, namely the X of two different intersection complexes are just 0. So yeah, so it will give the nice description of representation.
So that's description.
There are a lot of things I couldn't mention in time. Well, namely the associativity of convolution product is really deeply related to projection formula and base change. And I think there are no other ways to prove that. Almost no other ways.
If there are no more questions, I think this will.